Let's take a look at our homework from last night, page 569, number 2, 4, 6, 7, 9, and 10. Any issues with any of those questions? Besides maybe 10B that I probably should have waited to assign. Go ahead. 4A. Michael? Okay. 4A. Any others besides 4A? That's it? All right, that's not bad. Question 4A. You know what, let's do all of number 4 since we don't have a whole lot to go over here. 4A says, at a point in Earth's atmosphere, the electric field is 150 newtons per coulomb downward. The gravitational field is 9.80 newtons per kilogram downward. What's the electric force on a proton? What's the gravitational force on a proton at that point? Tell me right now before we do the question, which do you think is going to be bigger? The electric force or the gravitational force? There's no guarantees of this, but we can make a pretty good educated guess, I think, as to which one's going to be bigger. Yeah. The electric force is nearly always bigger than the gravitational force. All other things being equal, electricity is a stronger force than gravitation. We'll get a constant. We don't need to look any further than that. K is 8.99 times 10 to the positive 9. Big G is 6.67 times 10 to the minus 11. Electricity will almost always be a bigger force. All right, we have an electric field that is 150 newtons per coulomb downward. We have a gravitational field that is 9.80 newtons per kilogram downward. We want to find the electric force. We want to find the gravitational force. And we've got a proton. And of course, if we need the mass of the proton, the charge of the proton, all we have to do is check our data sheet for that. This proton, is it causing the field or is it experiencing the field? The electric field, that is. It says, determine the force on a proton at this point. So the field is 150 newtons per coulomb. The proton is at that point. Is that proton causing that field or is that experiencing that field? It's experiencing that field, right? Now, what's causing it? We don't know. We have no idea what's causing this electric field. It doesn't really matter. As long as we have enough information about the experiencer, then we can use the experiencer equation. The experiencer equation for electric field is F over Q. Now, we're going to rearrange that since we're solving for F. It becomes Q times E. The proton charge on your data sheet is 1.6 times 10 to the minus 19 coulombs, and the electric field strength is 150. When we multiply those together, we end up getting 2.4 times 10 to the minus 17? 2.4 times 10 to the minus 17, and the units on that would be newtons. So my electric force, 2.4 times 10 to the minus 17 newtons. Let's find our force of gravity now. My force of gravity is m times g. M times the gravitational field strength. That ultimately comes from the rearranged equation for gravitational field, right? G is equal to F over m. You guys found the gravitational force a million times last year in Physics 20. It was always m times g. The mass here is 1.67 times 10 to the minus 27 kilograms. That's on your data sheet if it wasn't given to you in the question. G is 9.80 as opposed to 9.81. When we do the math on that one, it's going to work out to be something like 1.6 times 10 to the minus 26. I don't know the exact number there, but something like that. Pretty close to that. Michael told me when I asked the question before we actually started doing it, which one is going to be bigger, he said, I think that the electric force is going to be bigger. And it is. It's quite a bit bigger, right? 10 to the minus 17 compared to 10 to the minus 26. It's 10 to the 9 times bigger than the gravitational force. And that's not a big surprise to us. The electric force is almost always bigger than the force of gravity. I'd like you to take a look at a couple multiple choice questions now. These are 47 and 48 on our worksheet booklet. The information that goes with 47 and 48 is up on the board right now. I'm going to leave that up on the board. I want you to take a look in the booklet to see what the question 47 is. Read through the information. Read through the question. I'll tell you right now, you can boil this question down to a couple simple little things. That's what I want you to do. Read through this, Strip away all that stuff that doesn't matter, boil it down to a couple simple little things, solve the problem. Okay, give you a minute or so to do that, and then we'll take a look at it as a class. Now let's take a look at it. Now let's read through the information. Let's try to strip away as a class here what doesn't really matter and kind of interpret how to make this into a simple, straightforward question. It says, in an automobile, a transformer is used to produce a high voltage that causes sparks in the spark plugs. A simplified automobile electrical system is shown below. A lot of people, when they look at this, say, hey, I kind of have some kind of idea as to how this works because they know something about cars. A lot of other people look at it and say, I have no idea about anything inside the engine of a car. I have no idea what this is about. Okay, it doesn't matter which perspective you're coming from. Okay, you're able to do this question even if you know nothing about cars. It goes on to say the 12-volt direct current battery is connected to a switch called the breaker points that turns the current in the primary coil on and off. So it says the primary coil is the one that's connected to this 12-volt power supply. Let's label this. Okay, this diagram is confusing to you. Let's make it less confusing by labeling it fully. This is the primary side. Now it goes on to say the required voltage of 20,000 volts is induced in the secondary coil. If I had to make a guess, I would guess that this part over here is the secondary coil because it's all that's left. But let's keep reading just to make sure. The secondary coil is connected to the distributor, which distributes the electrical voltage to each of the spark plugs. So, in fact, it is connected to the distributor, so this is the secondary coil. We will label that secondary. It tells us in the secondary coil that the potential difference is 20,000 volts. And it also tells us that the gap between the electrodes of the spark plug, the distance between one electrode and another electrode of the spark plug, is 2.00 millimeters. The distance between them, 2.00 millimeters. We probably should circle that millimeters, reminding us that we've got to convert that to meters if we have to use that number somewhere. In the question 47, we wanted to find the electric field in that little gap. In that little gap in the spark plug. Now, can we assume that it's parallel plates? Can we assume that it's a uniform electric field? Well, it is a relatively uniform electric field in there. Can you assume that? How do you know that? Well, you have nothing else to go on. If you have nothing else to go on, it's pretty clear, I think, that in this case, that it is a uniform field. They're giving us delta V. They're giving us delta D. We're solving for E. The only thing we can go with is the uniform field equation, E is equal to delta V over delta D. So let's use that. 20,000 volts divided by the distance of 0.002 meters, or 2.00 times 10 to the minus 3 meters. We do the math on that, it works out to be 1.0 times 10 to the 7 volts per meter. That should be an option for us there. I think if we take a look at the actual question, 1.0 times 10 to the 7 works out to be option D. How many people got that one? Okay. It's a tough question in one sense. You look at all this information, say, I have no idea what any of this means. I've never done any of this stuff with a spark plug or a transformer or whatever. From another aspect, we look at it and say, look, if I can sift through all that stuff that doesn't really matter, this becomes an easy question. We want to find the electric field. We have the voltage, the potential difference. We have the distance. We do the division. That's what I want you to be able to do. Okay, when you see this question, don't panic. When you see this question, don't get overwhelmed. Just read it. Okay, skim it and look at things that can make it a little bit simpler and turn it into that simple question that we just ended up doing. Okay, I'd like you to take a look at 48 as well. 48 is asking you for the acceleration of the electrons across that gap. Let's take a look at it here. Anytime we're looking for the acceleration of physics 30, what do we almost always do? What's the first thought that should come to our mind when we want to find acceleration? F equals ma. Okay, that's no different here. We want to use F is equal to m times a. We're going to rearrange it, of course, to solve for a. A is equal to F over m. We don't know what the force is, though. We do know what kind of force it is, however. What kind of force do we have here? What type of force is it? Is it a gravity force, a magnetic force? What kind of force is it? Electric force, right? How do we get the value of the electric force? We're going to have to get that some way. Well, we know that we have an electron that's experiencing that electric force. So let's use the experiencer equation, E is equal to F over Q. Let's rearrange that to solve for F. It becomes Q times the electric field strength. The electric field we've already solved for in the last question. It's 1.6 times 10 to the minus 19 coulombs times the electric field of 1.0 times 10 to the 7. Question? Is there a question, Chris? Michael? That's good? All right. We multiply those together, we end up getting 1.6 times 10 to the minus 12 coulombs. That's our force. That's our electric force. Now the question is pretty easy. The electric force is 1.6 times 10 to the minus 12 coulombs. The mass is, because it's an electron, is 9.11 times 10 to the minus 31. Where do we get that mass from again? It's on our data sheet. We do the math on that, and I think it works out to be 1.8 times 10 to the 18 meters per second squared. Now, they want it expressed as A decimal B times 10 to the CD. We're going to express it as 1.8 times 10 to the 18, or 1818. If they want it expressed as B times 10 to the W, we would write it this way, 1.8, and then we would end it right there. The value of B is 1.8. They're not asking us for the exponent if it's B times 10 to the W. They are asking us for the exponent if it's A decimal B times 10 to the CD. That's right, if they ask for it in that notation, right? They're asking for A, B, C, and D. So this is the correct answer to that question. Like this? No, if they want the decimal point in there, it'll be a B times 10 to the W. Now, normally when it's B times 10 to the W, they don't ask you for the value of W. No. No, if they want the value of W, they normally ask it this way, A decimal B times 10 to the CD. Or it might be A decimal B C times 10 to the D if it's a one-digit answer. Make sense? All right, we've just done two questions that I think are doable questions. It's in a difficult context, but the concept is not that bad. What we have to do is not get caught up in the context. We have to get caught up in the concept. Okay? Some people look at these questions and they just get lost in the context. Okay, don't. Okay, if you're going to get lost in something, make it the concept. Okay, if you're going to get something wrong, at least have it be something that you just don't get. You don't get a question wrong just because you didn't read through the question carefully enough or turn it into an easy question. This is tomorrow's quiz. Calculate the acceleration of the electron that's between two oppositely charged parallel plates 10 centimeters apart if the plates have a potential difference of 100 volts between them. You want to find the acceleration of an electron between two plates, given the potential difference between them, and given the distance between the plates. How is that question different than the two questions we just did? There's no context. That's it, right? The concept is exactly the same. You could do that question, you will do that question that we just put up there on tomorrow's quiz, and you will do well on it. So let's turn this question into that. Let's turn this into that quiz question. It's the same thing. Don't get bogged down by the wording. Just answer the question that's being asked. All right. Let's review what we did yesterday with conductors and electric fields, and then let's finish up the last little bit of that we have to finish up. And then that'll be it for the day. Besides just a little bit of homework, of course. I said besides a little bit of homework. When you have a whole bunch of extra charges on or in a conducting object, those extra charges will want to reach a point of static equilibrium. They are not initially in a point of static equilibrium. They can be anywhere, moving around, doing whatever. But they all experience a repulsive force due to every other extra charge that's present there. You get a whole bunch of extra electrons, they all repel each other. Eventually, they'll reach that point of static equilibrium, that point in which all of the forces end up balancing out. When that happens, these charges won't be moving anymore. If the forces are balanced, the charges are going to stay where they are. Every charged object, every object that has extra negative charges and therefore has a net charge, will eventually reach this point of static equilibrium, including the charged sphere. This charged sphere that we looked at yesterday has 3 extra electrons. It could have 30,000 extra electrons. The analysis would be exactly the same, but the diagram would look a little bit more complicated because you'd be drawing arrows everywhere you turn around. We got 3 of them just to simplify the diagram a little bit. Charge number 1 experiences 2 forces. It experiences a force this way because of charge 3 and a force this way because of charge 2. The net force acting on charge 1 ends up being this way. Charge 2 experiences 2 forces, a repulsive force caused by number 1 and a repulsive force caused by number 3. The net force acting on charge 2 ends up being this way. And finally, charge 3 experiences, once again, 2 repulsive forces. One of them is caused by charge 2. One of them is caused by charge 1. The net force as a result of 1 on 3 and 2 on 3 ends up being this way. The net force on each of these 3 extra electrons ends up being in which direction? All 3 of them are pointing toward the outer surface. These electrons are therefore going to go which way? They're all going to go to the outer surface. Now, why don't they keep going? Once they get to diagram B here and they're on the outer surface, why don't they keep going beyond the outer surface and just leave this charged conducting sphere? What's out here? Usually it's going to be air out here. The electrons don't want to go into the air. They'd rather stay on the conductor. They're free to move around on the conductor. They're not free to move around in the air. So they're likely going to stay on the conductor unless you get too many electrons here. If you get too many of them here, then they repel each other too much. There's too strong of a force of repulsion, and that charged conducting sphere can't hold all of the electrons. So some of them at that point will discharge. Some of them at that point will arc to the air, and you'll lose electrons. We'll assume, when we're doing a problem like this, that the charges will go to the outside and they'll stop there. What do you notice about the distribution of charges on the outer surface there? They're evenly spaced. They're equally distributed. They're equidistant apart, we say. Okay, the next one we did yesterday was when we had a solid, flat conducting plate. Same kind of idea here. It's a nice uniform surface. It's not curved like the last one, but it's uniform. It's not pointy and all jaggedy. Here we have 3 electrons, 3 extra electrons. The first one experiences a force caused by number 2 to the left. It also experiences a force caused by number 3 to the left. It ends up experiencing a net force to the left that's quite large. The force on number 3 is to the right. It's caused by number 1 and caused by number 2. It's smaller because charge 2 is further away from 3 than 2 is from 1. The force on number 2, caused by number 1, is to the right. Caused by number 3 is to the left. The force of 1 on 2 is bigger because 2 and 1 are closer together than 3 and 2. What happened to this charge in the